In his latest book, The Universe Within, Discovering the Common History of Rocks, Planets, and People, Shubin asks even bigger questions, and he details the cosmological evolution of our species. But wait, cosmological evolution? What does that even mean?
I wanted to follow a timeline of the history of the cosmos, origin of the universe, origin of the planet, origin of the solar system, function and workings of the planet, and see how portions of our structure and our bodies relate to each of those events and cosmologic history. So that was the idea, just generalizing from there.
One thing I was curious about is why, as an evolutionary biologist, was Shubin writing about space? Well, it turns out that all roads lead back to Carl Sagan.
And because I've had an abiding interest ever since I was a kid in astronomy, and in fact, if I wasn't a paleontologist, I'd probably be an astronomer. So I've always been interested in it, and it was hard as growing up as I did, and seeing Carl Sagan and Apollo moon missions, really not to think about the cosmos and the solar system, and about how important they are in our own history as a lineage, and if you follow that lineage all the way from the atoms that make us. And so what this book was sort of an extension of Carl Sagan's great theme, which is we are stardust, but then taking it to its logical extensions, right? I mean that history is manifest in our bodies, and it's seen in connections we have with everything from the orbits of Jupiter to the formation of the moon to the workings of the atmosphere and the planet itself.
Carl Sagan is one of my personal heroes, so...
You choose your heroes wisely.
Speaking of stardust, did you know that for every 400 million atoms of hydrogen I have in my body, I only have 1 atom of cobalt? And sadly, even though my tissue is made up of a massive amount of carbon and oxygen, it doesn't have any helium, which is the second most abundant atom in the universe. Where did these atoms come from?
If you look at the history of our bodies, so the atoms that compose us, the material basis, is largely derived from the first million years after the Big Bang, which is the smallest atomic nuclei, hydrogen and its cousins, and to the stellar evolution processes, which include the fusion reactions that occur in diverse kinds of stars, and then the supernovae, which happen for a variety of reasons. And each one of those processes combine nuclei. As we know in fusion reactions, smaller bits make larger bits, but not, the whole doesn't equal the sum of the parts, that enormous amounts of energy are released. So it's that combination that produces the periodic table of matter in our universe and the periodic table of matter in our bodies. The periodic table of matter in our bodies, that subset that exists in us, doesn't include unreactive elements, obviously, because we thrive by the hydrogen bonds and the diverse bonds that exist among atoms, but also the electron trades that happen, which much of our energy budgets are based on. So each of those particles arose after the Big Bang in the first million years. So after the Big Bang, you have the rapid expansion period of where you have the rapid expansion of the universe, and then cooling to the extent where different parts of our universe that we know and love come into being, right? First the forces, then the matter versus antimatter balance. Fortunately, matter, so there's a slight imbalance there, and so we have matter and we exist, which is good, I hope. And then then the subatomic particles, then the nuclei, then the smallest atoms, which are the hydrogen atoms and lithium and things like that. And then later recombining in stellar processes. But that took gravity, that took other larger forces to come into being, or larger entities. So if you look in our bodies, we have a chemical and atomic structure that relates to the universe and the cosmos, and we have a biological structure that relates to the planet and its interactions with the other planets in our solar system.
So we've moved on from the atoms in our bodies, which are unimaginably tiny, to our solar system, which is relatively big. So this made me curious, why is our solar system a particularly good place for life to form? Shubin had a really great answer for this.
Well, it's not just our solar system, but it's our place in it. So the Goldilocks phenomenon, which we all read about. We're at the right distance from the sun for the right balance of heat and size and mass to allow liquid water and plate tectonics to occur, which provides the stability for life to evolve. I mean, life requires a degree of, it requires stability and change, but stability is a big piece of that. You know, we can't be like Venus, which is super hot. We can't be like other planets, which have, which have a fixed rotation where they have a hot and cold, they have the dark side and the light side. So, basically we are the right distance from the sun of the right sized planet for life to have evolved. Now, when you think about our solar system, our place in that solar system and where our planet formed is really dependent on the other planets that formed there. Remember, the formation of the solar system is such that what you had is a dust cloud that was swirling the forming sun, and matter was accreting. The gravitational attraction of matter was accreting to produce the planets of our solar system. But there's a competition for matter. And the 12-ton gorilla here is Jupiter. That's the one that is most massive and exerts the largest gravitational pull on our planet. So that not only the formation of Jupiter not only influenced the size of our planet and the position of our planet, but it also influences the orbit of our planet in very regular ways, which have shaped much of biological evolution.
I feel like I've read that Jupiter also attracts asteroids and
Oh, you
things
bet.
to itself to protects the Earth in some way.
Yeah, exactly. So there's asteroid belts and there's rotations of asteroids. So there may be a statistical properties of Jupiter that affect the collision of asteroids on Earth, which have themselves affected evolution. So when you think about, there's some grand interconnections in space and biology. I mean, when we think of it as biologists, I mean we see those connections, right? When you're a biologist, you see the evolutionary connections among mammals, people, fish, worms, and flies. We work in them every day. But in the same manner, we see, as we look deeper in time and broader in space, what we see are deep connections that have influenced our evolutionary past with Jupiter and the moon and other places and other things like that.
So I got pretty excited when Shubin mentioned the moon because, well, our moon is a little weird. It's really big compared to the size of our planet, and it gives us the tides, and, well, it's beautiful. But where did the moon come from? And how has it shaped life on our planet?
Well, the moon is, let's just think about how important the moon is, other than just, the romantic, The moon affects the tides of Earth, so we are a tidal planet, right? And much of Earth has that rhythm in us. The moon defines many of the basic rhythms that life lives by. I mean, the tidal and monthly rhythms, but as well as the diurnal rhythms. Because the spinning of the Earth is obviously the light-dark cycle. But that is matched because of the physical relationship of the rotation of the moon and the spinning of the Earth. There is because of conservation of angular momentum and energy and so forth, the orbit of the moon affects the spinning of the Earth. They're locked in a tidal, and they're locked in a particular way. So what that means is the cycles that we are all know and love, the daily cycles, the monthly cycles, the tidal cycles, really come about because of the Earth-Moon system. And it's even probably more than that if you believe one of the consensus stories, theories, hypotheses for the origin of the moon. There are a number of reigning hypotheses for the origin of the moon. The one that seems to have the most empirical support at the moment is the big whack, right? The idea that a large Mars-sized asteroid hit the Earth back in the early evolution of the Earth, about 4.4 billion years ago, 4.5 billion years ago, and that spalled off dust, both vaporized that asteroid as well as vaporized crust of the Earth, which later congealed as the moon. And there's a fair amount of evidence to support that. The chemistry of moon rocks, and the comparison to the chemistry of Earth rocks, properties of the orbit of the Earth. But one of the sequelae of that theory is that not only did the moon come about in that big thwack, but the tilt of the Earth did too. So if that's the case, then the origin of the moon is related not only to the cycles that we live by with, the diurnal cycles and daylight, the tidal and monthly, but also the seasons. So those are the fundamental clocks inside our bodies, and all animals are tuned to those in many ways. Some very subtle, some very profound and deep. And that's where the Earth-Moon system lies in us.
The moon is unusually big for a moon.
Oh, it's
as
huge.
far as we are aware of, at least.
Yeah, and it's that exactly compared to Jupiter and Saturn relative to the size of the Earth. And I think that's one of the supporting arguments, with the mathematical models that lie behind the the big thwack theory. It accounts for the mass of both bodies.
What did the thwacking? Was it an asteroid or
Yeah,
was it
Mars-sized
a
asteroid.
Mars-sized asteroid?
Yeah, you remember, the early congealing solar system was, dust surrounding the sun that, ever larger clumps are forming. Well, those clumps are knocking into each other, and this is thought to be one of the consequences of those knocks. But, one thing we learned about in biology, right? It was one of the Biology 101. What do you learn about? You learn about circadian cycles. You learn about circadian clocks, the genes, period, and timeless, and all these. Those are really fundamental properties of animal life, and, the rise and fall of DNA, protein and DNA activity through the functions of these diverse genes in flies and people and hamsters, happens on a diurnal cycle. So much of our biology is tuned to these cycles, and we take a lot of it for granted. And one thing I wanted to do in a general book was to tell those stories, which are kind of obvious to a working scientist. We all learn about circadian rhythms, and we all learn about how fundamental they are to molecular biology. But most people don't know that, and most people don't know how much of our biology is clock-like properties at the base of it, including much of the physiology of our organs.
That's true. It's something that we understand intuitively, but we might not think about. Really.
Yeah, and I'll make you a bet. I'll make you in 10 years' time. I think chronobiology will be a very active field of medicine because the more we look, the more we find that our health depends on these things. And so. And again, thank you, the moon, right?
Yay, moon.
Yeah.
It used to be much closer to the Earth.
Yeah, it's moving away. So that's another argument for the big thwack theory. The moon is moving away, is getting more distant with each passing day. And as a consequence of that, and as a consequence of the relationship of the Earth to the moon, the Earth's orbit the Earth's spinning is slowing. So today is 2 milliseconds shorter than yesterday, which is 2 milliseconds shorter than the day before.
Amazing.
Yeah, and if you calculate that, it turns out we've lost. The days are getting longer, and the years are getting shorter in terms of number of days, right? And you can calculate that using certain fossils. Actually, fossil corals have little cycles inside them, where you can tell them the light-dark cycles, and you can count them up, and you can see that there were more days in a year 400 million years ago. And the reason why there were more days in a year is not because the year is longer in any great sense, but it's because the Earth was spinning faster then.
I also really like to imagine how big the tides must have been when the moon was
closer.
close.
Exactly. And there are rocks called rhythmites where you can see the tides and you can see their rhythms. The one thing we can't do is it'd be cool to do, to see what the relative height of those tides were, back in the Devonian compared to today. We can look at their cyclicity, which is great because then we can compare that. And there's some cool rocks even in the Midwest where we can see those, like tombstones in Indiana. But we don't know that. We don't know. And we could predict how big those tides would be. But it'd be great to be able to see it in the rocks,
Yeah.
But you can't.
So sadly, it was time to move away from the moon and return to the Earth. So I asked Shubin to describe one of the most influential geological events that's occurred in the history of our planet and how that's really shaped life here on Earth.
Yeah, so if you think about, there are many. I mean, in terms of those that have affected life, take one that's fairly obvious to all of us, and that is the glacial interglacial cycles.
Okay.
That is, you cannot be an evolutionary biologist working in temperate forests in Canada or wherever and, not think about the glaciers in terms of understanding the glacial interglacial periods define, the waxing, the movement of life, the evolution of life in certain parts of the Earth. Northern Europe, Midwest, I mean, it's such a major factor in evolution, including human evolution. And I think when you look at not only the distribution of animals but major selective pressures on them, the glacial interglacial cycles have been one of the dominant sort of forces and overprints on those, like environmental. Well, those, as we know, are in part related to orbital variation. That is, our planet has an orbit that varies from circular to more elliptical. The tilt and wobble of the Earth vary, and these things have cycles. 100,000
So the axis of the Earth wobbles a little.
Yeah, exactly. And these happen of regular intervals. So there's a 100,000 year cycle of eccentricity in a circuit. There's a 40,000 and 20,000 year cycles superimposed on that of wobble and tilt as well. Well, you think about those patterns, and if you superimpose them, they produce a prediction, a quantitative prediction of when you would have likely glacial and interglacial periods. Based on those orbital properties, you'd have different amounts of heat, transporting through the Earth in different ways. And as a consequence of that, a prediction was made back in the several decades ago that the orbital variation should match largely the waxing and waning of the glaciers we see, the interglacial period. Well, it turns out that cycle is largely there is an effect of the orbital variation. Some of these cycles have a very dominant effect on the glacial and interglacial periods.
Wow.
Yeah, and that was a really triumph. That was a great triumph of geoscience back in the 70s and 80s. Showing that the cyclicity predicted by what are called Milankovitch cycles matches to an order, a first order of approximation to the glacial and interglacial periods.
Wow.
Which is really good. There's still a lot of puzzles in there because it's complex, because it's not just the orbits, but it's also how heat is transferred in the Earth. It's those ocean currents and tidal currents, but there's still a signal, a very noticeable signal to these. Anyway, so the waxing and waning glaciers is related in part to the orbital variation of the Earth over regular cycles. Well, that itself, what drives that orbital variation? Well, it's the interaction of our planet with Jupiter.
Oh,
Right,
Jupiter
of course.
again.
Right, what else would do it? Right, it's
Yeah.
Jupiter again. So, in a very real sense, if you follow the chain of logic, it makes total sense each step along the way. Oh yeah, evolution in glacial interglacial periods. You can see that. Glacial interglacial periods. Yeah, we can see how that's related to orbital variation. Oh yeah, in orbital variation, how that's related to Jupiter. But when you take the endpoints that our planet's interaction with Jupiter has affected biological evolution, it seems utterly strange.
Yeah.
But then when you follow each particular step along that chain of logic, it's like, wow, okay, I believe that.
Yeah, you see.
So that's one of the stories I love to tell, because that really directly shows how, in a very tangible way, biological evolution is something we can actually see around us, including in our own bodies, relates to orbital variation, which relates to Jupiter. But there are others as well. If you think about, if you believe some theories, and there's one very powerful hypothesis out there, controversial, but supported by a lot of data, that is the rise of the Tibetan Plateau. When India smashed into Asia, that was a climate-changing event, and that climate-changing event really affected evolution in certain major ways. And that's another story that shows the relationship between mountain building and continental movement, the atmosphere and climate of the Earth, and biological evolution. The key thing, the one that I wanted to drive home in the book, is that there are great connections that we see, that we know as scientists, that have a lot of evidence to support them. And then when you put them all together, they really take you to kind of mind-blowing places.
Yeah.
That mountain building may be related to, and continental movement may be related to evolution and climate, and that may have influenced our evolution as a species. That Jupiter has such a great impact on us. And that the moon is so important. I mean, when you see these things, the evidence is there to support it, but it's kind of like, oh, wow. I mean, when you think about it. So I loved writing about it in the book.
Yeah, it really drives home the improbable nature of our existence. It depends on so many of these things just being perfect.
Yeah, exactly. I mean, and right. It took so many things for to be perfect, to be sitting here with you today, right? Everything just had to go perfect. My son had to get better. I had to be at the right.
Yeah.
So you know what I mean. You can say that about everything that exists, but because it's everything, when you add up all the events that had to happen, it's just so unusual. It's the craziest thing in the world that I actually walked to work today. Right. Richard Feynman used to tell a story like that.
Well, I think it's a nice attitude to have.
It seemed fitting that my question about geological events on Earth led right back to the Moon and Jupiter. But thinking about these cosmological events, the Big Bang, exploding stars, the vastness of our universe, made me wonder what the future might hold for our peculiar bipedal pie-loving species. I asked Shubin what his thoughts were on this.
I think we're screwed. Okay, so in a word,
Yeah.
no, but I mean in the long time scale. I mean, frankly, our planet's doomed. We're gone. It's done, and it's not because of human effects. It's because the sun's going to go red dwarf.
Yeah.
It's going to take all the water off the planet. So just like individuals are born, live, and die, this planet is going to be born, live, and die. There's going to become a point when it's no longer habitable for life.
Right.
Now, we're not going to be here, and probably our species won't be, but and indeed our solar system and galaxy has a life too. So everything is born, lives, and dies. They're all individuals. So in that sense, yeah, it's dismal. Now maybe Enceladus, moon of Saturn, or Europa, moon of Jupiter would be habitable for life, but certainly the Earth won't be at that time. Now before then, the relevant question is, what's the prognosis? Well, again, let's just take another time scale. One thing you learn as a paleontologist is that every species goes extinct. I mean, it's a fact, okay? Species are born, live, and die, and ours will have a beginning, middle, and an end. It's just what that end will be, I mean, will that end be transmutation into another species, or a set of species, or will it be, extinction? I have no clue about that. Now, before that happens, let's talk about that. I'm more optimistic in the short term. So, long term, it's kind of dismal. But in the short term, yeah, I mean, I think one thing that we have is the power to change our biology and the power to really impact the planet in both negative and positive ways. And that's kind of scary. But it does offer some. If you're an optimist like I am, it could offer some hope. That is, just as medicines have been important for diseases, I mean, antibiotics and our eyeglasses and so forth, that we've been able to extend and enrich our lives by technology. I see that increasing. Now, that's not to say that's the panacea, but frankly, if you were to look, if you were to ask the question, if we were to come back in a time machine, you and I, in 3,000 years, and sort of look around and see what do people look like, and what do they do, what guides their performance, what guides how long they live, how they think, how they run, how they ride a bicycle. It's going to be technology, right? I mean, it'll be drugs and devices that are going to be extending our performance as a species. And I think we're only going to get better than that, right? Neurobiology, I mean, as we learn more about the brain. Cell biology, as we learn more about cell death and aging and disease. I mean, it's just inevitable that the quality of life will increase. Now, that doesn't mean we as people won't find a way to screw it up. So it's not just technology, but it's access to technology that'll make a difference. And we stand a very real chance of living in a world where we will cause a speciation event, if you will, among different kinds of humans based on technology. Because if you think of a world of haves and have-nots, we already have a world that's kind of shaped like that. The potential of one class of humans is very different from the potential of another class of humans. The cause of death of one class of humans is very different from another set of classes of humans. I mean, most human beings die of infectious diseases, things that actually aren't that common in a society that we live in. Which our diseases are diseases of old age, cancers and cardiac problems and things like that. It's not malaria and diarrhea that kills us. So I mean, we're already seeing that impact, and I think unless we take care, we will see an ever increasing divide. Now, that need not happen because technology does have a way of getting cheaper, and more accessible.
That's true. Yeah.
If you go to, I just worked in Ethiopia a few months ago. Everybody has a cell phone. Everybody. I mean, they're more plugged in than we are in some ways. I mean, because so technology's gotten significantly cheaper. So I mean, I'm not painting an entirely dark picture because I'm just painting an unpredictable picture.
Right.
Universe is an unpredictable place.
Yeah, and that's what you learn about evolution. It just doesn't. You kind of know what the parameters are going to be, but I can't tell you what it's going to look like in 4,000 years.
You never know when an asteroid is going to
whack
us again.
Exactly.
Well, here's hoping that we don't get thwacked anytime soon. Well, at least not until the next